on YouTube that I would make a review or just kind of like working out problems for the Texas A&M Don't Panic Physics 206 Exam 2 2019. That was a mouthful. But I thought I would just work through this exam for the hell of it and upload it to YouTube. Because I always was like, the solutions are maybe not vague, but they don't really do work through. They don't really work through the exam to show you what the examples are and how to get the answers. So I thought I would go ahead and just do that as a study guide for myself and maybe help somebody out in the future. So I'm currently 3 Modelos deep. It's been a rough semester, but we're gonna do this exam. So let's fucking do it. Okay. So let's see this first question here, and I have done this exam already, so don't be impressed. But we've got an object of mass m moving along the x-axis, having velocity to the left with magnitude v1 x8. Okay, so the only force acting on the object is given by the equation, as you can see there. And so the question's asking if it's conservative or not. And so the law we're most likely going to use for this question, if I remember correctly, is the potential energy law, or law of potential energy. So conservative forces have potential energy functions. Non-conservative forces don't. But since so what we can do here, this law is going to just go ahead and be, we're going to just write this law as, so the potential energy of a function or of a force is equal to the negative integral of that force, dr, I think. Yeah, and so that's what we're going to use here. There's going to be another law we use, but so far we can just go ahead and say that we have that. Okay, so it's asking us to determine whether or not the force is conservative. So what we can do is we can take that, and I'm just going to integrate this in my head, but the negative integral, and also it's important to realize that this is going to the left. This force is going to the left. That means it's in the negative direction. So I'm going to go ahead and make this positive. Right? Okay, so what I mean by that is we're going to take the negative integral of plus c1x plus c2x cubed dx. Okay, and so you can just kind of exchange that dr for dx because we're only working the x direction, so it doesn't matter. So we're going to go ahead and integrate that, and we get that it's negative c1 over 2x squared minus c2 over 4 x to the 4th power, plus some constant value, which will go away. But so we know it's conservative because when we take the negative derivative of this function here, we get our force back. And so if you can go back and forth like that, then it's a conservative force. Okay. So now it's asking, determine whether or not this force is conservative, and then find the kinetic energy of the object at x equals a over 2. So we know that we're at a, first and foremost. So we're going to be integrating along this distance. Right? So the law we're going to use for that is we could use the law of conservation of energy, since we only have this one force working on this object, and we know it's conservative, so we can use the law of conservation of energy. And so that's going to be k plus u equals k final plus u final. And so that might be an incorrect way of saying it, but that's basically just saying E initial equals E final, right? And energy equals kinetic plus potential energy. So we're just going to have, we're starting at A, so we know that it's moving to the left with a velocity of v1, magnitude v1, sorry. So we know its velocity at first. So the initial velocity is going to be 1/2, or the initial kinetic energy is going to be 1/2 mv1 squared. Okay, because that's kinetic energy. And then we're going to have the the potential energy here is going to be minus, oh Lord, oh, my bad, I already made these negatives, so this is going to be positive. Apologize for that. So we have, I made this negative because it's going to the left. The force is pointing to the left, so it's negative in the negative x direction. So, so we have kinetic energy plus c1 over 2 a squared, because that's where we're starting, because x is position, plus c2 over 4 times a to the 4th power. Right, and that's going to equal the kinetic energy at a over 2, which is what we're solving for. So you don't even have to write that. Plus what the kinetic energy would be at a over 2. And so that would be a over 2 squared, or potentially at a over 2, which would be, a over 2 squared plus c over 4, or c2 over 4, sorry, times a over 4 to the 4th power. Okay, so that's going to be, we can work that out. You can have K, E, kinetic energy, and so you have C1 times A, or C1 over 8 times A squared, plus C2 over 4 to the 4th power. Oh my god, sorry. That's going to be, oh wait, sorry, that's 2 to the 4th power. 16 times 4 was 64. I was a little confused there for a second. So 64 times a to the 4th power. And that's going to be equal to C1, C2 over 4, a to the 4th, plus C1 over 2, a to the squared, plus 1/2 mv squared. Okay, so then we're going to do, we're going to bring this over, and you end up getting that KE at a over 2 is 1/2 mv, mv1 squared, plus C1 over 2 times a squared, plus C2 over 4 a to the 4th power, minus C1 over 8 a squared, plus, or minus C2 over 64 a to the 4th power. Okay, so I don't know if I have the answers pulled up here, but we can check this out. Answers from 2019. Okay, so yes, as you can see, we have the right answer, and you can, combine these terms together if you wanted to, but I'm not going to. So I would leave it like this, and just put that in the results section. So there you go. That's the first question there. Okay, so that's not too bad. We use conservation energy and potential energy. Okay, so moving forward. This question is: a box of mass m is placed on at rest on an inclined plane, known angle theta. A known horizontal force of magnitude p is applied to the block, and so the coefficient of friction between the block and the plane is this. And so that's annoying, but that's not too bad. So, assuming the block slides down the plane, finds velocity at point x equals L over 2. Okay, so that's not bad. Let me a sec. Excuse me. So our first step here would make a free body diagram. That's what I would do. That's what the great physics professors tell us to do, right? Now listen to them. And so this is going to be really bad, free body diagram. But okay, so we have our forces acting on this object. We have our gravity force down. We have the normal force up. And then we have this horizontal force, P. And then we have our friction working against this object, right? And so we've got a little bit of everything going on here. So I'm going to go ahead and decompose this gravity force. So we've got gravity here at an angle theta. And then we have P, the force P, going over here. And that's going to be pointing up and down, also at an angle theta. And so we got P here, and we've got gravity here. Okay, so what we're most likely going to be using here is since we have friction, and friction's a non-conservative force, we're going to most likely be using the work energy theorem, which is that the work total equals the change in kinetic energy. Right, so we'll go ahead and take that here in a second here. Okay, so we have. So one thing we also want to do is we want to solve for the normal force, because the forces that are going to be doing work are gravity. So we have gravity doing work. We have P is going to be doing work, and so is friction. Friction's also going to be doing work. And so for friction, we know that friction is going to be equal to mu n. So we got to figure out what n is. So in the y direction, we have that we've got mg cosine theta, because this would be the y direction. And then we have the p sine theta equal to may, which is just going to be 0. And so we have that the normal force equals mg cosine theta plus p sine theta. And this is a good disclaimer. Anybody that knows me personally and is watching this video, yes, I did wait till my senior. We did wait until my senior to take physics, but there's a good reason for that. Maybe, but anyway, so the normal force is going to be this, right? And so, if we want to just run over here real quick, we can start applying the work equations. And so the work done by gravity from 0, because we're starting at 0, to L over 2, that's going to equal, we want to do this in the x direction, so we're going to have mg sine of theta, and it's in the positive x direction because we've got, I forgot to put our little free body, our coordinate system here. And so we've got our diagram here. Right, so we can go ahead and get that going. So d theta, or a dx, sorry. And so that's going to equal, mg L over 2 sine theta. And for anybody that's a little shaky on calculus, all I did is add an x and evaluate the integral from L 0 to L over 2. And so that's what this is going to be. So we have our that's our work done by gravity. Then we're going to have our work done by P, which is going to be 0 to L over 2, right? And so we know P is just going to be negative P cosine of theta, because we have that, P is in this horizontal direction, so its x component is this, and so that's the adjacent angle. The adjacent side to theta, and so we're going to have that it's negative P L over 2 cosine of theta. Okay. And so there we go. Now, friction is going to be a little annoying, but it shouldn't be that bad. So we have 0 to L over 2 again, and we know that friction has this coefficient here, right? And so we're going to have mu naught 1 plus x over L, right? X over L, yes. And then times mg cosine theta plus p sine of theta, which is a constant, dx. Okay, so all we're really going to be doing here is we have that, this integral essentially is just going to be x plus x squared over 2L times mu naught mg cosine theta plus p sine theta. And that's going to be evaluated from 0 to L over 2. So here we have that this x is just going to be L over 2. And you could essentially isolate this because, if you just had x from L half zeros, it's just going to be L over 2. Right. Oh, Lord. Okay, so L over 2, right, plus L over 2 squared, which is going to be, let's just do this on its own. So we have 1 over 2L times x squared evaluated from L over 2 to 0. Okay, so you're going to have 1 over 2L times L over 2 squared, which is just going to be 1 over 2L times L squared over 4. So L over 8. Right, the math's right. Yeah, if you had L squared over 4 over 2L. Over 2L. 8, that cancels out. Okay, yes, it would be that. Okay, so it'd be L over 8. And I'm going really fast, but this is physics, not calculus. Sorry. So we have L over 8. I believe. Yes, that makes sense. Okay, so times mu naught mg cosine theta. Okay, so we can just kind of change this to 4L, so that's going to be 4L over 8, so 5L over 8 is going to be our value here, plus p sine of theta. Okay, cool. So then we're going to just add all these together, right, and use this theorem here. So we're adding all the work together. So we have mg over 2L sine of theta minus p over 2L cosine of theta plus, oh, and I apologize, friction's negative. That makes sense. So we're going to have negative 5L8 times, that whole thing. Mu mg cosine theta plus p sine theta. Okay, so then we have that, and this is going to be equal to the change in kinetic energy. So it starts at rest. So the final velocity is what we're looking for. So mv squared minus 0, since it starts at rest, since there's no kinetic energy at the start. So we're looking for this v final. So really all you have to do is multiply all this by 2. So if you come down here, we're going to end up having mgl sine theta minus pl cosine theta minus 5L over 4 times mu naught mg cosine theta plus p sine theta. Okay, so, and then that's going to be equal to mf squared, and so we can just kind of take this, divide it by m, remember this is still equal to that, and then take the square root to get the velocity. Okay, and all I really did was cancel out the 2's by multiplying it, getting a 4, then dividing by m over to the other side, and then taking the square root. And so this is our value. Now, if we go back to the answers, that looks pretty similar to me. It's a little nicer looking, but, that's how you get that. So, let's see. Let's check out this next question. Let me just take a drink quick. Okay, so we have, let me read this real quick. Let's see here. We have that in order to give a spacecraft an energy boost, they use the slingshot effect in which the spacecraft interacts with the planet, which can be considered a perfectly elastic collision, which means that energy is conserved. So this can be understood by considering the interaction of the light spacecraft MS with some heavy object mass m, where the actual force exerted by the object on the spacecraft is not specified. Assuming the heavy object continues in its original direction after the interaction, obtain enough equations so that you could solve for the magnitude of the final velocity of the spacecraft and the final direction of theta given the magnitude of its initial velocity and its initial direction. So we just need the equations for this one. So this shouldn't be too bad, actually. So if I remember correctly, we want to use conservation of momentum here. So so that would just be, total momentum equals, well, actually, I don't know exactly what the law is here, but we'll as we work through the problem, we'll get back to that. Okay, so what we want to do is we have that. Oh man, okay, so this spacecraft with some heavy object mass in, where the actual force exerted by the object on the spacecraft is not specified, assuming the heavy object continues in its original direction after the interaction. Obtain enough equations so that you could solve for the magnitude of the final velocity of the spacecraft VF and the final direction, given the magnitude of the initial velocity V1 and its initial direction. Okay, so what we want to do here is we know that the massive object has has momentum mass times velocity Vp. Okay. And since they're not getting attached to each other, we want to say that, okay, so momentum in the system here, the conservation momentum of this system. And so this object is moving in the positive x direction. Yes, okay, now everything makes sense. The small object has velocity v1 at this angle theta with the horizontal here. And so its x direction is negative v1 cosine theta. And so its momentum is going to be small s times v1 cosine theta. Okay, so that makes sense. What we want to do here is then set that equal to the momentum at the end, which would be the larger mass times the change in its momentum, because it will change after interacting. And then the new velocity for the smaller object is going to be at this angle theta final. And so its x velocity is going to be Vf cosine of theta in the positive x direction. Okay, so then that's going to add that. So we have Vf cosine of theta final. Okay, so that's the momentum of the system. Now, what we also need is the momentum of the object itself, the spacecraft. And so, we need the momentum in the y direction as well. Sorry, conservation momentum in the y direction as well. Okay, so the larger mass doesn't move in the y direction, so that's going to just be 0. But then the spacecraft moves in the negative y direction, which is ms times v1 sine theta, because then you have this angle here, or this side here, same thing here. And so that's going to equal 0 again, because the mass is not going to be moving. It's going to stay in the direction it was going. But then the spacecraft's going to have this new velocity in the y direction, Vf sine theta of f. Okay, well, actually, it's going to be negative direction. My bad. So, there you go. And so at the end of the day, you're going to have, they just want the equations, so we're not going to change anything. Now, the last thing we need is the energy of the system. Since it's elastic, we can use conservation of energy to figure this out. And we're going to need that because that's the only way you can figure out the final velocity. And so what we want to do here is we have that the larger mass is going to have a kinetic energy of Vp squared over 2. Because it's only moving in the x direction. It's not going to have any gravitational potential energy because we're in space, I'm assuming. And then the spacecraft's going to have its own kinetic energy and not its own. It's not going to have gravitational potential energy. And then this is going to be equal to the change in energy, or the final energy, which is going to be this next velocity that the larger mass takes on, plus the new velocity that the spacecraft takes on. And so these are our 3 equations that we could use to solve for theta f and velocity. So that's that question. That's not that bad. Oh, this question's really annoying, but we'll bust it out real quick. This one's a big conservation of energy question here. So the way we want to do this one here is let me get a reference guide real quick. We want to use conservation of energy in this question, which is not too bad. But essentially, we want to think about, the different points that this object. Well, let me read real quick. So the small ball of mass m is fired from a frictionless gun by compressing a spring by amount a. The gun is aimed at the angle theta as shown. At the highest point in the ball's trajectory, it enters a frictionless tube, which contains a spring with another constant k2. Find the velocity of the ball when it leaves the gun. Call the velocity v1. Find the maximum height reached by the ball. Call this height h. Find the amount. The second spring gets compressed. And so, the dead giveaway here is the fact that we're using springs, and that springs are conservative force, so we can use the energy, the conservation of energy. And so the way we want to do this is we want to consider the different points that this ball will be in the system. And so, for example, we have this is going to be conservation of energy. So K plus U, or energy I equals energy F. Not too bad. Now we also want to use the the potential energy of a spring, which the potential energy of a spring is 1/2 kx squared, where the kx is the amount it's compressed. Then we also want to use the gravitational potential energy, which is mg times y, or the height from the ground that it is. So we want to use those four sort of identities here, or equations. And so let's go ahead and do it. So when it leaves the spring, or when it's in the spring, or this thing, it's going to have this energy. Its energy there is going to be equal to its kinetic energy plus the potential energies. So its kinetic energy there is going to be 0 because it's not moving. But then it's going to have the spring force energy, or it's going to have the potential energy from the spring, which is k times a squared, because it's compressing the spring in amount a, right? And so there we go. And so then you want to also add the gravitational energy, potential energy, which is going to be mg times 0, because it's on the ground, so there's no potential energy there. And then we have energy 1 when it leaves the gun. That's important as well. So we have energy 1, or energy at point 1 when it leaves the gun. And so that's going to be, it's going to have a kinetic energy now of a velocity 1, because that's what it says it wants it to be. So velocity 1. So it's going to have 1/2 mv1 squared. It's no longer going to have a spring potential energy, or potential energy of the spring, because it's not on the spring anymore. So that's just going to be 0 plus the gravitational potential energy, which we can find by doing a little bit of trig here. So if this thing equals theta, and then this distance is a, this height here, the height's going to be equal to sine, or we have sine of theta is going to be equal to h over a, which means h is going to equal to sine theta, or sine theta of a sine theta. There we go. And so that our gravitational energy is a sine theta. Okay, so that's good. And then we also need its energy at the maximum height, which is at height h. Okay, so now we have energy 2, which is going to be 1/2 mv. It's not going to be mv1 squared now, because it's going to be at an angle. And so when it hits here, it's going to have this. We're going to be using the x component of its velocity, which if it is at an angle theta, again, that'll be cosine of v1, or the x component of v1 will be, we'll use cosine for that. So if we're looking at the velocity here, and that's right, that we want its x component and its y component. Here at this point, we would have this angle theta, and then this component here would be v1 cosine theta, and so that's the velocity at that point. So we want to use mv1 squared cosine squared theta, right? Because that's kinetic energy. It's not going to have a spring force energy, so it's just going to have it's not going to have the potential energy of the spring anymore, right? So then we're just going to have the gravitational potential energy, which is going to be mg times h. Mg times h. So, yeah, okay. And then finally, we want to find the amount the second spring gets condensed. So we're going to have our energy whenever it enters the other's tube, right? And that's going to be, it's going to have no velocity once it hits the other spring. So we can just go ahead and say that's going to be 0. Plus the spring potentials, the second spring potential energy. Don't forget your constants, as that's going to be a distance b squared plus the gravitational potential energy at that point, which is also going to be h, because that tube is off the floor a distance h from the ground. There you go. Okay, so these are our potential energy. These are our energy functions we're going to use to solve this stuff. So we use E0 and E1 to solve for part A. Right, and so we have 1/2 K1A squared equals 1/2 MV1 squared plus MGA sine theta. And so you just kind of move all this stuff over. Go ahead and multiply by 2, so we would have K1A squared minus MG, or 2MG A sine theta, all divided by M, and then take the square root to solve for velocity. Oh, okay, so there we go. Also equal velocity. That's all I really did there was multiply by 2 to get rid of the 1/2, then subtract this MGA sine theta over, divide by M, then take square root. Okay, there we go. Now B's asking for the maximum height reached by this ball, and so we want to know the difference between E naught, or not necessarily the difference, but we want to set E naught equal to E2. And so what we're going to have here is we have, again, I mean, we could also do E1 equal to E2, but there's more zeroed out terms here in E naught than there is in E1, so we're going to use that again. So we have 1/2 K1A squared equal to 1/2 MV1 squared cosine squared theta plus MGH. Okay, so then we're multiply by 2 again, so we get K1A squared equal to MV1 squared cosine squared theta plus 2MGH. We're solving for h, so we want to subtract this over, so K1A squared minus MV1 squared cosine squared theta equals to 2MGH. Guess I need to divide by 2, but we want to, seems like something's missing here. Kind of, but not really. This should still work, technically. We divide by 2mg to get over the side, and so we have K1 divided by 2mg, or we could just do 1 over 2mg times K1A squared minus MV1 squared cosine squared theta equals h. I mean, yeah, that I think that's right. I think it is. We could check in a second. It could be wrong, but I mean, that is in all terms of known proportions there. Yeah, it's fine. Okay, so then C's want us to find the 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 amount the second spring gets compressed. So we want to use E2 equal to E3, right? Okay, so then we have 1/2 mv1 squared cosine squared theta plus mgh. That's going to be equal to 1/2 k2b squared plus mgh. We can cancel out the mgh, right? And so now we just have, we cancel out the 2's as well. And now we have mv1 squared cosine squared theta equal to k2b squared. Now we can divide by k2. I think, well, well, yeah, I mean, that should be fine. Yeah. So you get mv1 squared cosine squared theta divided by k2. And then take the square root of that, and you get b. Now, this question isn't too bad, but I am looking at the answers. I'm not really looking a little different, but there might just be some substitution things that you have to do. It's looking like, oh, I see. Yeah, so mv1 squared, we solve that to be, I mean, I guess that's not necessarily that important in the long term, because I mean, you can just plug those values in. I could be wrong though, but all it's really saying is that we did find out that the kinetic energy of this thing is equal to 1/2 k1a squared minus mg a sine theta, and it's wanting us to plug it in to these values here, wherever it may be. But these are technically correct, just not substituted for that specific value. But all in all, I mean, this is supposed to be a guide, so we got close enough. But yeah, okay, so that's exam 2019, exam 2 2019. So I'm gonna get another Modelo, and maybe I'll do another one and upload it before Wednesday when this exam actually happens. But yeah. Thank you for watching my second YouTube video.